$60 bucks. One plastic pipe from the hardware store. No compressor, no refrigerant, no electricity worth mentioning. 5 feet under your feet. Right now, the ground sits at a steady 50 to 54 degrees. Summer, winter, doesn't matter what the thermometer says above ground. Always. You catch that number? Sit with it for a second, because it's the whole video. Engineers have known this trick for over 100 years, documented in technical journals nobody outside the field ever reads. The Persians were doing a version of this 3,000 years ago, out in the desert, with nothing but clay and stone. And the HVAC industry pulls in tens of billions of dollars a year selling you a fix for the exact same problem that this thing solves for free. Forever, no bill, no contract, no technician visit. So it's genuinely not something that industry is ever going to point you toward, and honestly, why would they? By the end of this video, you're going to know exactly what this is, how it actually works down to the physics, and how to build one yourself this weekend. Most homes, especially in colder climates, are basically built for winter first and everything else second. Thick walls, decent insulation, tight double-glazed windows, all of it engineered to trap heat inside and keep it there. And that's exactly what turns into a genuine problem the moment summer shows up. The same insulation that saves you real money in January traps heat, like a lid clamped down on a pot in July. The air inside gets stagnant, the walls and ceiling soak up heat all day long like a battery charging, and then slowly release that stored heat at night when you're trying to sleep. Your attic can hit well over 100 degrees on an ordinary August afternoon without anything unusual happening at all. Weather data confirms the number of genuinely hot days each year has roughly doubled in a lot of regions since the 1950s, and in some areas it's tripled, with the trend still climbing. So, what does almost everyone do about it? They buy a portable AC unit. It sits in the bedroom, hums through half the night, pulls close to 1,000 watts continuously, and adds a couple $100s to your summer electric bill before it's dead and sitting at the curb 3 or 4 years later. If you want to do it properly instead, you get a real split system installed, outdoor condenser unit, wall penetration, professional installation, and that's easily $3,000 to $5,000 per room with a licensed contractor doing the work. Wait times for installers have been genuinely brutal the last couple years too, sometimes months out. Add in ongoing maintenance, refrigerant top-offs when it inevitably leaks a little, filter changes, and a basic service call running you $150 a visit, and over 20 years you're realistically looking at $8,000 to $15,000 total for cooling one single room. And then you get to buy an entirely new unit anyway because nothing lasts forever. So your house, every summer, becomes a heat battery working directly against you. Walls, ceiling, roof, all of it charges up during the day and doesn't let go of that stored heat fast enough once the sun goes down. You're basically living inside a slow, self-heating oven, and the entire cooling industry has exactly one answer for that problem. Pay for power, get some cold air blown at you. Here's your bill, see you next month. But what if the dirt sitting quietly under your own backyard already has the real answer? One that's worked reliably for thousands of years across completely different civilizations, and one that an entire multi-billion-dollar industry has zero genuine interest in ever telling you about, because there's simply no invoice attached to it. To understand why this got buried, you've got to look honestly at who actually profits off your discomfort every single summer. The HVAC industry is a genuine heavyweight, tens of billions of dollars a year in trade revenue alone, and a growing chunk of that specifically comes from cooling equipment as summers get hotter. Walk into any big hardware store and look at the split units on display. Cheapest one on the shelf starts around $800 before installation is even factored in. Installation alone tax on another $1,000 to $2,000. Then, depending on where you live, you legally need a certified technician to commission the system because of refrigerant handling regulations. Look at an actual contractor quote sometime. It's usually a multi-page document. Outdoor unit placement, wall penetration work, refrigerant line routing, condensate drain installation, electrical work, and the total circled at the bottom starts around $3,000 for a single room. The industry, when you really look at it, doesn't sell you cooling. It sells you a subscription wearing a different outfit. You buy the physical unit, you pay for the install labor, you pay the electricity bill every single month it runs, you pay for maintenance visits, and about 15 years later you buy an entirely new unit and the whole cycle starts over from scratch. If you want more of this kind of practical, forgotten engineering, subscribe. It genuinely helps keep this channel going. Now, back to the actual story. You might be sitting there thinking, if a genuinely cheap alternative to AC actually existed and actually worked, wouldn't everybody already have one installed by now? That's a completely fair question, and it happens to be exactly what a major building physics research institute has spent years actually studying in the field. Their measurements consistently show that passive, ground-based cooling systems deliver enough real cooling capacity for residential buildings across most temperate climate zones. Documented, measured over multiple years, published in peer-reviewed literature, just never advertised on television, because there's genuinely nobody positioned to make sustained profit off a hole in the ground. This story doesn't start in a modern engineering lab, though. It starts in the desert, thousands of years before anyone had a word for thermodynamics. Over 3,000 years ago, Persian engineers built tall wind catchers out of sun-dried clay that caught the hot desert wind and funneled it downward through underground stone channels carved beneath the buildings. Down there, roughly 5 to 10 feet below the blazing surface, the earth held a steady, boring, reliable temperature all year round, regardless of what the desert sun was doing above ground. The air cooled measurably as it traveled through those stone channels and flowed straight into the living spaces of the building. No compressor anywhere in the system, no refrigerant, no moving parts to wear out or replace. Just earth, stone, and basic physics quietly doing exactly what physics has always done. The Romans, independently developing much of their own engineering tradition, understood the same essential principle. In their villas scattered around the Mediterranean coast, they routed intake air through underground channels before that air was ever allowed to reach the interior rooms. Pliny the Elder actually wrote about techniques like this in the 1st century AD, describing it as fairly ordinary building practice for anyone who could afford to build properly. And here's where this stops being ancient history and becomes directly, immediately relevant to you and your own backyard. There's a building tradition going back centuries in cooler climates too, one that basically every old farmhouse and every vineyard property once had as standard equipment: the root cellar. A room dug straight into the earth where food stayed reliably fresh without a single watt of power involved, because the temperature down there simply never moved much regardless of season. 50 to 54 degrees, summer and winter both, no exceptions. That's the exact same number from the very start of this video, and that's not a coincidence. This underlying principle actually has a formal engineering name: an earth-to-air heat exchanger, sometimes just called an earth tube. A pipe buried in the ground that uses the Earth's naturally steady temperature to cool incoming air before that air ever reaches your house. Engineers have documented this technique in technical journals going back to at least the 1920s, treating it as legitimate, unremarkable building science. A major technical university had working experimental installations running as far back as the 1960s, gathering real performance data. Passive building research institutes have recommended earth tubes as a standard component of energy-efficient design since their founding decades ago. This technology was never secret in any meaningful sense. It was never banned anywhere. It was never disproven by anyone with real data. It just quietly stopped being profitable to talk about out loud. When energy got genuinely cheap in the 50s and 60s, and the air conditioning industry started mass-producing affordable units for the first time, interest in the ground itself as a cooling source basically evaporated overnight. Not because it stopped working, the physics obviously didn't change. Because there was simply no recurring money in it for anyone to chase. Nobody sat in a room and conspired to bury this knowledge on purpose. That's genuinely not how these things tend to work in the real world. Knowledge that stops being profitable doesn't usually get formally outlawed or suppressed. It just gets shrugged at, quietly deprioritized, and slowly forgotten across a generation or two. And a technology that literally nobody can own, meter, patent, or license is a technology that no industry on Earth is ever going to spend real advertising money promoting to you. Now here's where the actual measured numbers get genuinely impressive, and I want to walk through them carefully because they're the whole case. A major building physics institute measured earth tubes under real, uncontrolled outdoor conditions over multiple full years, not a lab simulation. With a pipe roughly 65 feet long buried around 5 feet deep, Incoming outdoor air on a 95-degree summer afternoon drops down to somewhere between 60 and 68 degrees by the time it exits into the house. That's a 15 to 19-degree swing, achieved with zero compressor anywhere in the system, purely from sustained contact with the surrounding ground. National Weather Services track soil temperatures at that depth across entire countries. And depending on your specific region, the yearly average sits somewhere between 48 and 54 degrees, only swinging a modest few degrees across the entire 12 months. In the dead heat of summer, when it's 95 degrees baking your yard, the ground 5 feet down is still sitting calmly around 54 degrees, completely unbothered by what's happening on the surface. The only meaningful power draw in the entire system is a small fan, somewhere between 10 and 30 watts, which is genuinely less than a basic desk lamp uses sitting on your table. Compare that directly to a typical split AC unit pulling 800 to 2000 watts continuously while it runs. We're talking roughly a 50 to 100 times difference in power draw between the two systems. Engineers measure cooling efficiency using something called COP, coefficient of performance, essentially how much cooling you get per unit of energy spent. A standard AC unit runs a COP somewhere around 3 to 4, which is genuinely decent for mechanical refrigeration. An earth tube can mathematically hit COPs in the 20s to 40s range. That's not a modest improvement you'd round up in a sales pitch. That's an entirely different category of efficiency, barely comparable on the same chart. Long-term university research has documented earth tubes running for multiple decades without any measurable drop in performance over time. The ground fully resets itself every single winter automatically. The cooling source recharges completely on its own, for free, forever, with nobody doing anything to maintain it. Energy efficiency agencies formally list earth tubes as a recognized, legitimate method of passive building cooling, not as some fringe alternative therapy for houses. Modern energy codes in a lot of places actually give measurable credit for passive cooling systems in a building's overall official energy rating. This isn't some hack circulating in a forum somewhere. It's officially recommended, quietly, by the people who study building efficiency for a living. 50 degrees, year-round, sitting directly under your feet the entire time, doing nothing, costing nothing, waiting. If you've made it this far into the video, you're probably not the type to just scroll past and forget about it. You're someone who actually builds things with your hands. Now for the question everyone eventually asks once they're seriously considering this. What about condensation? What about mold building up inside the pipe? Genuinely fair question, and I'm not going to skip past it. When warm summer air moves steadily through a meaningfully cooler pipe, moisture in that air condenses on the interior walls. Exactly the same physics as a cold glass of water sweating on a hot day. Building physics researchers have documented straightforward, unglamorous solutions for exactly this problem. A 2% downward slope built into the pipe run, plus a proper condensate drain installed at the lowest point, handles the moisture completely on its own. Add a simple mesh filter at the intake to keep debris and pests out, and the problem is fully solved, as long as you plan for it from day one of the build rather than trying to patch it in afterward. In regions with naturally elevated radon gas levels in the soil, and some regions genuinely do have higher background levels than others, you'll want properly sealed pipe connections throughout the run. This is standard practice on any decent perforated foundation drain pipe that already comes with rubber gasket seals right out of the box. So it's not really an extra step, just something worth being deliberate about. Worth checking your local geological survey data either way, before you commit to a location. I also want to be honest with you about what this setup does and doesn't do, because overselling it helps nobody and just leads to disappointed comments later. This system works best in climates with real seasonal temperature swings and reasonably dry summers, where the ground genuinely stays cooler than the air for a meaningful stretch of the year. In extremely humid, swampy climates, the cooling effect is still real but noticeably smaller, and you'll be fighting moisture management harder throughout the system. This also isn't designed to fully replace central air during the single most brutal week of summer in an already hot, humid region. It's genuinely better understood as a way to dramatically cut how hard and how often your existing AC has to run, potentially eliminating the need for it entirely in a lot of moderate climates, while taking real pressure off it everywhere else. So now you've got the complete, honest picture in front of you. On one side, a split AC system running $3,000 to $5,000 installed, plus ongoing electricity, maintenance, and refrigerant costs stacking up every single year, fully replaced entirely after about 15 years of service. On the other side, a plastic pipe costing under $100 in materials that last decades in the ground and never once sends you a bill of any kind. No maintenance contract to sign, no refrigerant to ever top off, no monthly power draw worth mentioning on your bill. The industry sells you the first option because they genuinely profit off it, not just one time at purchase, but every single summer for as long as you own the house. Nobody profits off the second option in any meaningful, recurring way, so unsurprisingly, nobody's out there actively marketing it to you on television or in your search results. This is usually the exact part of a video like this where someone tries to sell you a course or a downloadable guide. I'm doing the opposite of that. Here's the complete, full build free. Right now, you need standard corrugated PVC drain pipe, 8 inches in diameter, the orange perforated stuff sold at literally every hardware store in the country, running you roughly $4 to $6 a linear foot. You'll want somewhere between 50 and 80 feet of it depending on your yard size and layout. Add connector couplings for joining each length together, a 90-degree elbow fitting for the outdoor air intake, another elbow for the entry point into the house itself, a piece of filter mesh secured at the intake opening, and a small inline duct fan to move the air. A simple 12-volt solar-powered fan works genuinely well here and keeps the whole system fully independent of your home's electrical panel, or a basic inline duct fan running $20 to $30 does the job just as effectively if you'd rather hardwire it. Total material cost for the entire build lands somewhere around $60 to $120, depending on run length and which fan option you pick. For the actual installation, dig a trench roughly 5 feet deep along your planned route. Yeah, it's genuinely real physical work, no point pretending otherwise, but it's a realistic weekend project with a shovel and a wheelbarrow if you're doing it by hand, or half a single day if you rent a small mini excavator, which is often worth the rental fee. The pipe itself needs at least a 2% downward slope maintained along its entire length, which on a 65-foot run works out to roughly 16 inches of total elevation change between the high end and the low end, something worth marking out with stakes and string before you start digging blind. At the lowest point in the run, install a proper condensate drain, and a simple gravel-filled dry well handles this job just fine without needing anything fancy or purchased. Backfill the trench using the same dirt you dug out originally, and tamp it down lightly as you go. No special engineered fill material is needed anywhere in this process. The ordinary ground you already have sitting in your yard is your heat exchanger, doing the real work. At the house itself, route the pipe through a wall penetration or an existing basement window well, bringing it cleanly into the building envelope. Seal that penetration point properly using a rubber sleeve and expanding foam to keep the whole system airtight and pest-free. On the permit question, most local jurisdictions don't require a formal permit for digging in your own yard as long as you're not touching or altering the structural foundation of the house itself. But check your specific local codes and building department directly to be sure, since these rules genuinely do vary quite a bit by location, and it's a 5-minute phone call that saves potential headaches later. Here's a detail I deliberately held back until now, because it only really matters once you've genuinely decided to move forward and build this yourself. Position your air intake on the north side of your property, somewhere in consistent shade if possible. That single choice stops direct sun from preheating the pipe right at the intake point, which would otherwise quietly cut into your cooling effect before the air has even reached the ground to begin with. And if you decide to bump the pipe diameter up from 8 inches to a full 12 inches, you roughly double your total airflow capacity for only a modest, genuinely reasonable bump in material cost. Picture this for a second, because it's honestly what sold me on actually building one. It's August, 96 degrees outside, thick heat sitting over everything. Your neighbor's got every blind shut tight, and their AC unit has been running nonstop since sunrise, straining audibly. You just flip on the small fan for your earth tube. It's quiet, almost genuinely unhearable from another room. Within a few minutes, air measuring around 62 degrees is steadily flowing out of the vent into your living room. No hum, no uncomfortable draft, just cool, dry air that smells faintly, pleasantly of earth. Your utility bill has no line item anywhere for cooling that month. No service contract sitting with some HVAC company. No scheduled maintenance call to book. Same story again next summer. And the one after that. And 20 years from now, still the same story. The ground under your own yard never once sends you a bill. It genuinely never has, not to anyone ever. The people who dug root cellars 200 years ago with hand tools didn't know the first thing about coefficients of performance or formal energy audits. They simply knew from lived experience that the ground stayed cool even when the sun was genuinely brutal overhead, and they knew exactly how to put that fact to practical use for their families. This knowledge was never secret in any real sense. It never sat locked behind a paywall or a certification exam. It never needed a licensed technician to legally touch it. It just needed somebody willing to pick up a shovel and actually start digging. At some point along the way, most of us collectively just stopped doing that. Not because it ever quit working. The physics never changed one bit. Because somebody else eventually offered us a more convenient bill to pay instead, and convenience, understandably, won out for a while. The ground under your own feet hasn't changed one single degree since then. It's still sitting there right now, quietly waiting at a steady 50 degrees, exactly like it always has been. If you're into this kind of forgotten, genuinely practical engineering, the stuff that actually still works today whether or not anyone's selling it to you, subscribe to Forgotten Ways. The next one's already coming, and based on the comments from the last few videos, I don't think you're going to want to miss it.